Folks, we are going to keep trucking on and on and on with these example problems because we're on a roll and we're not going to stop. So, by the end of this lecture video series, you are going to be a pro. You're going to be an expert on these types of carbonyl reactions that we have grouped together, that we have classified as type 1 carbonyl reactions, because that's what all of these have been so far. So let's continue on with type 1 reactions. We've already talked about slews of them, and we'll keep going and we'll keep using what we have learned in the upcoming example problems too. And you're going to see they're no more complicated than what they were or what they have been before. All right, so here, let's do a CH3, a CH2, a carbon, double bond O, that's supposed to be a carbon, to an oxygen, to a carbon, to a double bond O, to a CH2, to a CH3. And let's add on, in this particular example, an amine, because we really haven't reacted an amine with an acid anhydride yet. We have used an alcohol, we have used water, but we haven't really used an amine structure. So let's take a look at CH3 and maybe NH2. So there is an amine, and we've got to figure out what happens. What goes on, if anything, what goes on in this mechanism and to generate a product. So just like before, there is no difference, folks, on the mechanism. The mechanism has stayed the same. So what we have is a nitrogen with a free pair of electrons. That nitrogen, because of the free pairs of electrons, is a negative source area. That negative source area is what we call a nucleophile. That nucleophile is going to go through and it's going to attack the carbon of the carbonyl or the acyl bond. That carbon's going to shove those electrons up, and then that oxygen's going to shove those electrons down, and that carbon then has a choice to make. What does it do? All right, so let me redraw the product, or redraw the reagent that we're starting with first before we make our products. So here's my C double bond O, O, C double bond O. There's my anhydride piece. And now what we have done is that we have added a nitrogen, but that nitrogen has brought everything to the table. So here is my N and my H and my H and my CH3, and that fourth bond is going to go to the carbon. Just like before, that overloads nitrogen. That's not very good for it. It doesn't want that to stay around. So it wants to get rid of the positive charge so it can become neutral, and the only way that it can do that is get rid of a hydrogen. So just like before in all of the other examples, folks, we had an H and an OH. I told you to split down the middle, and the OH went on to that carbon of the carbonyl. With the alcohol, when that was concerned, we did the same thing. We had this alcohol. I told you to split down the middle, and that hydrogen went off, and the OCH3 went on to the carbon of the carbonyl. And the same thing happens with amines. We've done a couple of these examples already. So basically what that means is that you take a hydrogen and split it off of the molecule, and the rest of the group goes on to the carbon of the carbonyl. All right, so this is where we are at this moment. But we are only at the step where the oxygen shoves the electrons back to reform the double bond, forcing carbon to determine what leaving group needs to be kicked. Carbon has a decision at this moment, and it is okay with the decision. It doesn't think very much about the decision because it's all about the outside. It's about how pretty these groups are. Therefore, it's about how good of a leaving group these molecules are going to be. All right, so with this carbon, what it has to do here is it's got to figure out which one is going to be the better leaving group. Is it going to be this O with a carbonyl, which is our ester piece? Or is it going to be this nitrogen-containing compound that we identify as an amine? Well, I don't even have to look at the chart, folks. I don't even have to look at it because I know that amine group is at the bottom of the chart. It is the Miss America of them all. So that carbon is going to keep that nitrogen around. And that's just by default, very easy breezy reactions with amines. This is what goes on. So that carbon makes a decision to cut that bond off. And what we have left here is an amide at this point. So we have a carbon double bond O to a nitrogen. So that is an amide that we have forming a product. All right, so now what we've done is that we've erased this bond, and no longer are they connected to each other. So the only thing I'm going to do is squeeze this in just a little bit, because we've got to figure out, well, what happens here? We can't just have a negative oxygen floating around, can we? Okay, well, normally what happens is that this amine group brought that hydrogen that it had to get rid of. That hydrogen now, bink, off to the races it goes, out in the street, all alone, nowhere to go. And that hydrogen sees that negative oxygen, and they fall madly in love. So what we end up with is a OH that happens at that molecule in the very beginning. That is what goes on. So there's nothing different here that we've done. It's been the same thing, the same rehash over and over and over, but we have to be careful, because let's take a look at this. We already know that amines are kind of weird, because we often put a 2 out in front. So do we have to put a 2 out in front with a reaction with an acid anhydride? So kind of think about the product that we're forming, and that will tell you whether or not we need to do this. So with this particular type of reaction, an acid anhydride with an amine group, to make an amide, right? This is my structure of the amide. There is a problem. The problem with the amines before in the past is that they would always generate these acid byproducts. And we said, hey, well, we'll fix this. We'll put 2 moles in front of the amine, and that extra amine would be extra base, and that extra base would react with the acids, and it would neutralize that out of there. So we don't really have complications when it concerns our major products that get formed from this reaction down here. So do we do that here? Well, yeah, we can. And what that does is that it forces the majority of the reagent to go to the product side. Okay, well, we have extra CH3NH2 that is left over at this point. So this is all of the extra that did not get used up. Well, are we really generating something like HBr or HCl? And the answer is no, we're not really doing that here in this step. This acid is not getting formed because there was no chlorine there on my reagent to produce that byproduct. The HBr is not getting formed because there's no bromine on that reagent in order to form that product that we have to neutralize out. However, we are generating acids. What? What do you mean? Okay, well, if we take a look at this structure, and I told you, identify the functional group, you would look at this and you would say, oh, C double bond OOH? Well, that's called a carboxylic, acid. A carboxylic acid here, folks. So this is a little different. The reason it's different is that this would be regarded as a byproduct. This is forming that extra amine is actually going to attack those acids. It kills it out. It neutralizes it. So that way we don't have too many complications. Well, it just so happens that the acid anhydride that we are using here, that we typically use, no matter what type of anhydride that it is, will typically cleave on one side of these carbonyl bonds, and we always will end up with a carboxylic acid pretty much. But that is an acid. And the definition of an acid and the definition of the base do not change. We have acid here, and we have base that is here. And that base is extra base. Well, you might be thinking, okay, well, let's just stop. Let's not add the extra base. Okay, it's not that easy. And the reason that it's not that easy is because this base initiates the cleavage of this molecule into 2 pieces. When this molecule breaks off into 2 pieces, it makes these 2 molecules. And then that some of that methylamine will turn around, and any amine will turn around and react with the carboxylic acid that's getting generated at that moment in time. So we're actually hurting ourselves if we do not put the 2 there. And the reason is we're shortchanging our product. So this anhydride will break apart into 2 pieces. One of those pieces are carboxylic acids. Some of that amine will continue to break that down, but some of that amine will then start attacking the carboxylic acid. And if we do not put the 2 here in front, so it is required, if we do not put the 2 there in front and make us have extra, then we will not be generating enough product, because some of that reagent is getting used to destroy the product that we're forming over time. Okay? Now, if we have extra base, and we will if we do this reaction the proper way, the problem is that extra base will still react with the acid that is getting generated in the reaction. So this is a traditional acid-base reaction here. We can't stop it. We can't prevent it. It's just going to happen. So the definition of an acid is a proton donor, right? That was very general chemistry, chemistry 251, first week type of stuff. So this is going to spit off a hydrogen. That's the proton donor. If the environment has a pH greater than the pKa of the carboxylic acid. Well, the carboxylic acid's pKa's are pretty low. I mean, we're looking at like 4-ish here. And here we have an environment that has extra base. That extra base is an amine. And we know that these pKa's are about a 40. These pKa's are about a 4. That goes back to general chemistry. That goes back to the first 1 or 2 weeks of Orgo Chem 1. So because of this, it will donate the proton. We're putting it into a basic environment. So that will act as an acid. It will spit off the proton, and that proton's got to go somewhere. So where does it go? It actually goes to the base, because that's an acid-base reaction. The acid spits the proton off. The base takes up the proton. So this actually turns into a NH3, and it does carry a positive charge until it can figure out what to do with it. And because this does act as an acid, well, we erase that hydrogen off of there because it's not going to stay around. That hydrogen's going to be donated, and because of that, it loses a hydrogen, it loses a positive charge, so it actually will become a negative piece. So this is the proper products for this reaction. We have a carboxylic acid that was generated, but it turned into a carboxylate ion because this is now a negative charge that has a C double bond O on it. So that is a ester, and esters are OHs, so we can call these carboxylates. So that is a carboxylate anion. And that hydrogen goes and pairs up with the amine to make a protonated amine here. All right, so that is the breakdown of how the products get assembled. Now, if I want to go back and do a review of the nomenclature, what I'll do is that I'll name the amine. You know, we've done quite a few of the anhydrides already, so let's go ahead and name the amine again just to get some practice. So I named the group that's on the nitrogen first, and that is a methyl. So I need to write N-methyl. So that's how we will start that out. I find the longest carbon chain that amide is attached to. So carbon 1, carbon 2, carbon 3. So this is a propane. I drop the E and I add on the word amide. So N-methyl propanamide. Now, if I didn't want to do the propan, I could do a common name, propionamide, but we'll leave it here at the IUPAC name. All right. Now, the question that I always get, well, what if I forget to do this step? Okay, what if I put the hydrogen here and I just call it a day and I move on to the next problem? I tend to give you credit for that. Even though that you formally don't take it to the next step and realize that this is an acid, this is a base, they will do another reaction amongst themselves to create this negative and this positive piece. If you forget to do that step, I give you the benefit of the doubt. And I go ahead and tell you, okay, this is perfectly fine. If you want to leave this as a hydrogen, if you want to leave this as extra NH2 or maybe not even write it at all, I tend to give you credit for that type of answer because the majority of the correct answer is there. And again, I give you the benefit of the doubt on that kind of material. All right. Whew. All right, so let's go to our next functional group. And that next functional group is going to be an ester. Now, esters have specific reactions that they do as well. Esters do react with water. And when they react with water, and I've wrote it again as HOH, we call this a hydrolysis reaction. Lysis typically means cleave. In the world of organic, in the world of biochemistry, it typically means to cleave. And how are we going to cleave it? Well, we use hydro. And if you hydrate yourself, you drink water most of the time, or you at least should drink water. So hydrolysis or hydrolysis is the process of breaking down something, cleaving something, using a water molecule in order to initiate and complete that reaction. However, that's not the only thing that esters react with. Esters also react with alcohol groups. So this is something like an ROH. So we've handled alcohols before already. We've done them with acyl halides. We did them with the acid anhydrides. We also did waters in the same way. The story doesn't change here, folks. It's an ester. It's just a different starting point, but it's still an ester. It still undergoes the same type of mechanism because they're all type 1 reactions. So the alcohol is an ROH group, and that ROH group can be used to react with an ester. And guess what? We call this alcohol lysis. Yeah. So it breaks down using an alcohol. However, we also have another name that this goes by that most people use more often, and this is called trans-esterification. So trans means to change, right? It's changing something. Whatever that something is, you're going to be changing it. So it looks like trans-esterification basically means that we're changing the ester that we have. And that's pretty much what we're doing. And you'll see that in those reactions when we start doing them and I start giving you some examples of them. So hydrolysis, alcoholysis or alcoholysis, and trans-esterification, which is what it normally goes by. So each of these reactions that I have on the screen right now, they do require a catalyst because esters, we're getting further down on that nucleophilicity chart. So these esters are becoming more stubborn. They're becoming harder to react because that ester piece, depending on what we're reacting with it, is not so anxious to react like the other two functional groups were that we've talked about at this point. All right, so what kind of catalyst do we need in the reaction? Well, that's nothing more than just little o acid. That's all that's going to be. All right, so I bring in an acid with water, or I bring in the acid with the alcohol, and a reaction goes forward. And the answer is Yeah, this is something that we saw in Chemistry 251. If we took an alkene, which was a double bond molecule, and reacted it with water, we told you at that time that no really reaction takes place. We don't really get products. But if we initiate this reaction with a little bit of acid and water, then we do get a product that forms from that reaction. The same thing happened with alcohols back in the day. We said if we took a double bond, an alkene, reacted it with an alcohol, no reaction is going to go forward. But if we put it into the presence of H+, then we do get a reaction, and that reaction will give me a product. The same thing's happening here. Right? We have an ester that's a little bit more stubborn to react. We have to kind of coax it along a little bit, give it a jacuzzi tub, so that way it gets real loose and the juices are flowing, so that ester is more prone to react. And then we react that with water or alcohol in the presence of the H+. And we do get a reaction that goes forward if that goes on. All right. Now, there is a third reaction, and this third reaction, guess what, is with an amine. So we can react esters with an amine because that amine is at the bottom of the nucleophilicity chart. We know that it can come in. We know that it can substitute for things, and ester is no exception. So we do have an amine-related reaction that we can talk about with our ester groups. These amines, well, guess what we call these? We call these aminolysis. That was an amine cleavage. Cleavage. So lysis again means cleave, to break apart. What are we going to be breaking apart? How are we going to do it? Well, we're going to do it with an amine group, and that amine group is going to be a nitrogen-containing species. So there you go, folks. Those are the three reactions that we're going to be focused on with esters. So if you've noticed, what we're doing is we're going further and further down the nucleophilicity chart, and as we do that, our number of reactions are getting smaller and smaller and smaller. So let's start with the first one, and this is our hydrolysis reaction. So we're going to take an ester, C double bond OO, and let's just put a CH3 on this side, and we'll put a CH3 over here. That ester probably smells wonderful, as most esters do, right? And we talked a little bit about this. Esters are great flavorings. Esters are great scents that we can have around. It makes us smell good, but it also makes us smell like glue and skunk too. So we just have to pick out the right esters that we want to smell like. So here's our CH3, C double bond OO, and then on the other side of that oxygen is a methyl group, and we're going to react this with water, and we want to know what forms on the other side, if anything. Okay, well, here's the story. It's the same as what it always has been. So this water is HOH. That HOH, guess what? Has some free pairs of electrons. And guess what it's going to do? This free pair of electrons is negative. It's going to search and look for something that it can take advantage of. So it's going to find that poor little carbon wrapped up in all of these bonds here, and it's going to go hubba hubba, hey hey, buy me a drink. And that carbon says, okay, fine. So these electrons get pushed up, and oxygen says, oh no, not tonight. You're not. You treated me this way last weekend. You made me a promise, so you're going to keep the electrons this time. And carbon says, okay, fine, I'll do it. And then that carbon looks at these two leaving groups, and it's got to figure out what it wants. So at this point, what we have is a CH3 group with a carbon, double bond O, and then on this side is an OCH3, and then down here at the bottom, we have an OH and a H. Now, keep in mind that in the beginning is a protonated alcohol, but this is in the midst of getting eliminated, and this hydrogen goes away, So by the time that double bond forms, carbon now has a choice on what type of functional group that it wants to get rid of. So does it get rid of the OR or does it get rid of the OH? That is the question that carbon has to deal with. In all of the other examples, this kind of answer was pretty easy. It looked at the real ugly, nasty things that were on the chart and it said, you gotta go. I'm tired of waking up to your face every morning staring at me, slobbering all over those pillows and everything. It's disgusting. You gotta go. So that carbon really doesn't take any time at all to make up his mind on what he wants to do. But now the problem, because remember, I said that esters are very stubborn. So now the problem is that we have this nucleophilicity chart, and that's what we're seeing here. And this nucleophilicity chart has my OR group because that was part of the ester. And folks, that's down here at the very bottom. And then it has an OH group, and the OH group is right below it. Now you can imagine the problem that carbon has. I mean, it's got two good things going for it here. And on each arm, they're like trophy husbands or trophy wives, right? I mean, on each arm, it's got something that it is perfectly okay with. And it's not like one's super pretty and one's super nasty. Both of these are pretty much the same. So this is why esters tend to drag their feet a little bit, because they really do want to take their time to figure out, okay, which one do I want? But in this case, the OH group always beats it out because the OH group is lower on the chart. The OH group is a stronger base, and that makes the OR group in this case a better leaving group. So that is what we have to kind of remember when we begin talking about esters and their reactions. All right. So in this particular case, there we have it. We have that OH group that just came into that carbon, and we have that OR group, in this case a methyl group, but it can be an ethyl, it can be a benzene, it can be a propyl, it can be an isopropyl, it can be anything that it wants to be. It doesn't matter. And this carbon is going to choose to keep the alcohol. And that alcohol group is going to stay behind. And that means that bond goes away. So initially, this is going to carry a negative charge because this carbon is going to turn around and say, okay, out of everything, out of all my choices, sorry to do this to you. It's been great. It's been fun. But oxygen, you have got to go. And I'm keeping this new OH group that's coming my way. So that kind of completes the mechanism of the reaction. So here we have a C double bond OOH. So I know that this is a carboxylic acid that we have generated yet again. So I should be able to know how to name these. And then this OCH3 group, folks, what's going to happen to this? Well, that OCH3 group is swimming out there, but, you know, so is a hydrogen. The hydrogen's out there swimming too. You can't forget about the hydrogen. Where'd the hydrogen come from? Oh, the hydrogen came from the OH group because that was water that we used in the beginning. So that H plus sees that OCH3. They madly fall in love all over again. That gets rid of the H plus. That also gets rid of the O minus. And we form this group, which is an OH group. And that OH group is nothing more than an alcohol. So here, what we have is a ester, and that ester does react with water in the presence of some acid to get the juices flowing. We do need to put that in there, so there it is. I'll put H plus there. That ester will break apart. Lysis means cleave. And it will break apart into a carboxylic acid. We just got to know how to name it. And an alcohol. And once more, we just have to know how to name it. So if I go through and start assigning names to these, I name the group onto the O first, which is a methyl group. And then I name the two-component piece. That two-component is acete. and this is an ester, so that ends in -ate. So this is methyl acetate that reacts with water in the presence of acid to form, well, here's my 2-carbon chain, so acete with an ic and the word acid because it's a carboxylic acid. And then here, CH3OH, for goodness gracious, you should know what that is. And that CH3OH, that 1 carbon is a methyl group, and that OH is an alcohol. So those are all common names that I've assigned to these particular molecules or components. So if I go through and talk about the organic, listen up, brace yourselves. We have methyl acetate that reacts with water in the presence of acid. The water serves as the nucleophile to attack the partially positive carbon of the acyl group. The partial positive carbon shoves the electrons to the more electronegative oxygen. The electronegative oxygen reforms the double bond. That double bond, when it reforms, forces carbon to pick a good leaving group, which completes the nucleophilic acyl substitution reaction, because the carbon will force the ester component, or the OR group, to be the leaving group as it accepts the alcohol group. That forms acetic acid, which is a carboxylic acid, as well as methyl alcohol, which is an alcohol. Folks, there's organic, all wrapped up into a nice little neat shell. You remember back in Chemistry 251 when I told you, it's foundation, it's the fundamentals, you're going to be building on it. Well, look at what we just did. We kind of used an alkene reagent and catalyst back in the day. We went back, we learned how to name alcohol, so we had to dig that back out of the garbage of our brains that we've got. We had to go back and take a look at nomenclature on naming the products and the reactants. Folks, this is a whole chemical soup of different types of questions that just continue to build on and on and on. The other thing I want to say, notice we answered this problem simply knowing the mechanism. Simply knowing that one little mechanism has been able to allow us to solve every single one of these reactions that come through. Organic is not about memorizing methyl acetate plus water gives me this. No. If that is what you're doing, you're learning organic the wrong way. You need to put in perspective. This is a top 1 molecule, carbonyl. Top 1s undergo the same reaction. Double bond breaks, double bond forms, carbon has to choose a leaving group. What is the leaving group that's going to go away? That is what you need to be focused on. Not specific example problems and trying to regurgitate the products back onto a sheet of paper. You will never make it through organic that way. So hopefully with all of these examples, I keep repeating myself for a purpose, and that is instilling in your brain the mechanism of the type 1 carbonyls, because only after that, folks, can we really feel comfortable with these types of reactions that go forward. So in the next example, we'll pick up from here. We're not done with esters. We need to do some more examples before we go forward, but we're getting closer and closer to the end of this. So just bear with me. The light's right around the corner. I see it. It's shining. It's almost there. And then we'll be done with top 1 carbonyls. But folks, there's actually 2 more types. So just bear with us. We're almost done with top 1. We'll eventually get there. Your hands are probably cramping. Your head's about to explode. I've been there. I've done it. So be patient.